Now we have Marco Giuseppe Andreetta. Process parameters developed for different applications and relevance of open material system for jewelry additive manufacturing. Marco is graduated at Politecnico di Milano, and he has been dealing with 3D printing since 2006. He is a product marketing analyst at Sysma with a special focus on additive manufacturing in industrial sectors. The Sysma experience is that in order to have successful projects, we need a combination of skills of raw materials producers and application experts in order to have a systemic collaboration able to meet the requirements of customers. We need parameters, production strategies, and customized materials to meet the need of single customers. Marco, the floor to you.
Farò in inglese.
Come preferisci.
Il telecomando.
Questo è per girare le slide.
Questo qua.
Adesso sì.
Hello everyone, it's a pleasure to be here, and well, I will do this presentation in English just for the sake of also and the benefit of all the people that are following us from abroad. And I'm very happy to do this presentation after Professor Lowang-Watana, because I feel it's really a continuation of what is doing. Just few words about Sysma. Sysma, it's a company that was founded more than 60 years ago. It started as a company that built micro-mechanics for textile machines, and the first production plant was built in 1967. In 1976, that marked the beginning of the jewelry machines production. So since 1976, we are building machines for chain making. Over the years, the company expanded, and since 2001, we are using and integrating and building laser sources. And following this laser knowledge, we started working with 3D printing machines. We started building 3D printing machines in 2014, and we did this also with a joint venture with a German manufacturer, Trumpf. The company expanded over the years, and we built several new plants, and now we have our own headquarters in Piovene Rocchette. So just to sum up, the company has more than 40 years of experience in jewelry making machines, more than 20 years in laser manufacturing and laser-based process, and more than 10 years in manufacturing of metal 3D printing machines. So the first decision that we made when we started building 3D printing machine was that we wanted to have an open platform, an open system that could give freedom of choice and to our customers, and also to experiment with the parameters. The possibility to adapt building parameters, we think it's crucial for having good success projects, especially in the jewelry making manufacturing. So this is how we see the jewelry making, additive manufacturing for jewelry making. We start from the powder competence. We partner with powder manufacturers that can produce fine spherical powders for laser metal fusion. we know that for jewelry making, it's important to have a robust system, but also a system that can reduce material waste. Precious metals are getting more and more important. And then we have the process qualification. We develop laser and process parameters. All this harmonized approach may give parameters for building high quality parts with a very high density. We call it digital microstructure, so very fine microstructure that can comply with the jewelry high quality standards. And also we develop the parameters in order to have in order to be adapted to the post-processing. But this is a systemic competence that only gives a metallographic competence. We understand that what's needed is to have a partnership with application specialists that can fine-tune the parameters on the actual jewelry geometries, and then can finally deliver robust and predictable process for the end user. The benefit of having an open system, of course, is the fact that we can have different, really a lot of different alloys, and the list is growing. Now, I will start with the actual presentation. Of course, we partner with application and competence centers in all areas of the world that can really transform the parameters and the additive manufacturing in final products. So when we talk about building parameters, of course there's base parameters. So regarding laser, we have obviously laser power, scanning speed. Then there's hatching distance. We talked about this before. So the distance between all the laser paths. There's layer thickness. So the thickness of each layer that is being built. And then there's gas speed. But we focus on really a lot more advanced parameters, and we like to give our customers all the freedom to really fine-tune the process. So, for instance, when we talk about laser, there's, of course, laser power and scanning speed, but hatching, it's not just going back and forth with the laser, but it's also the ability to have different hatching strategies, different orders in the hatching, and also contours. Contours they make basically what's the external quality of the surface is like, and being able to vary all the parameters in the contours as well, it's really important. Bim Spot, we never talked about Bim Spot Size today, so we think it's important to choose the right beam spot for the right application. Whether the customer wants high quality, small geometries, or is more geared towards manufacturing. Layer thickness, of course, the customer needs to be free of choosing the layer thickness, but also different protective gas. An open system might give the customer the possibility to choose different grain size, different from what standard grain size distribution is. And then, of course, all the parameters, all the laser and hatching and contour parameters are also present in the up skin and down skin. So all the areas that are on the bottom or on the top of the part. So the advanced parameters are not only what happens inside the machine, but we like to think about all all that happens before. So when the customer designs a part or orient a part for additive manufacturing or design the supports, and all these parameters needs to be adapted to the actual post-production that it has been chosen. So no parameters, there's not a perfect parameters, there's only a perfect parameter for the actual workflow. So just to give you an example, this is basically 2 examples of 2 rings. So similar object, but different geometries, same material, but one has a really small cross section, and the other one is a massive component. You cannot use the same building parameters for these two objects. So a small part might have different validation criteria, so the surface quality needs to be as good as possible as built. There's thin wall section. So when we talk about advanced parameters, of course, we will take in account maybe the Bim Spot size. We will try to choose a machine with a small Bim Spot size diameter. Material, grain size distribution might be fine-tuned for the actual project, and the supports, as we discussed before, they will only need to have a supporting function. They're not anchoring the part. There's no need for heat management by the supports, and that's completely different when you're looking at the same object, so a ring, but a massive part. So in this part, the wall thickness changes along the geometry, and maybe the validation criteria changes. Build speed becomes more important. Maybe the actual value of this part, it's in massive production. So when we look at a part like this, it's still a ring, but we will choose a bigger Bim Spot size. The supports have a completely different value because they are managing heat exchange, and they are not only supporting the part, but also anchoring the part to the platform. And there could be some benefits from preheating to manage internal stresses, and adaptation of skin and core parameters, so different parameters from the outer surface and the inner surface in order to increase even more the build speed. So we looked at 2 different examples, 2 different rings, but they need completely different building parameters. Another example, courtesy of our partner Nuovi Gioielli. This is a textile built basically with metal additive manufacturing. In this technical example, what we see, there's no correlation with conventional technologies, so it's something really new, and all the part is completely interlaced. But in this case, parameters, they play a huge role in the being able to have the correct functionality of the part. So the part is not changed in the CAD file, but it's basically modified by the building parameters. So the actual dimension of each square could be changed and fine-tuned with beam compensation parameters. So basically the distance from the actual CAD file to the path of the laser. Now I would like to talk about titanium. It has been really a hot topic today. A lot of the people before me, they talked about titanium, and we think it's it's interesting because there's, first of all, a growing trend in jewelry regarding titanium, and it has some obvious benefits. It weighs a quarter of gold, so bigger items could be worn and still be comfortable. It's anti-allergenic, so it's let's say a medical grade material that is used also in jewelry making, also for this reason. For instance, titanium cases can be worn by people that are allergic to nickel. So in watchmaking, titanium could be interesting for this reason. And it could be processed, we saw in the presentation before, with a wide range of anodization, so in order to have really new and bold colors. So we focus on titanium because titanium, it's difficult to machine and process with traditional technologies. In traditional processing of titanium is really costly. Machining is really difficult and could also be dangerous sometimes. For those of you that are working a lot with milling machines, you know that probably titanium, you need to slow down the speed of milling in order to avoid unwanted hardening of the metal. So machining is slow. As we saw today from a presentation before, casting titanium as well is a very difficult task. And why titanium for the 3D printing? Well, titanium, it's not only an interesting material, it's one of the materials that can be printed more easily. So it's one of, I would say, probably the easiest material to print. And it's for different reasons. It's highly self-supporting. It really needs a small amount of supports, which leads to a small amount of post-processing. It has a relatively low elastic modulus, so the distortion during the process are limited. And a wide range of alloys are already developed for other markets. So if we look at all the alloys available, we have, for instance, titanium 6.4 in the grade 23. It's quite hard, so it might be difficult to polish manually, but it's really a benchmark material for all the additive manufacturing industry. We have titanium grade 1 and grade 2, so almost pure titanium. The hardness is lower, and it's really interesting for small shops, small jewelry shops. And then we have titanium 6.4 grade 5, really already widely used in the watchmaking industry, and it might be considered as a benchmark in the watchmaking industry. But for most of this application, the grade 23 might be the best choice. It's basically the similar in terms of chemical composition, but it's more pure in terms of oxygen and contaminant quantity. Then I would like to talk about a new alloy that has been developed by University of Trento. It's an alloy that has optimal biocompatibility. Of course, it's an alloy that might have a lot of interest for medical application. And but it has also optimal corrosion resistance. It's completely without vanadium, so it has optimal biocompatibility, but also can be in contact with the skin without without any issues. So the new material that has been developed by University of Trento, you can find the source form for their document here, and we did all the manufacturing of the samples, and we found that this new material has even higher buildability than conventional titanium 6.4, so it needs even less supports, and it's also a material that can be heat treated without using argon and at lower temperatures. So this is a comparison of titanium 6.4 grade 23 and this new alloy. Without heat treatment, we see that elongation is quite impressive. And with heat treatment, with simple heat treatment at only 650 degrees Celsius, it could reach and outperform titanium grade 23 in many ways. So this is an example of what can be done with this new alloy. So. Of course, the first application that comes to our mind was eyewear industry. It's an almost unbreakable material, but we think that the possibility to have new features like flexible designs in the jewelry, additive manufacturing, this could be a really interesting material. So. Just to wrap up, this is what we do in SYSMA. We focus on the development of new alloys for additive manufacturing. We are fine-tuning existing materials, but focusing on the actual geometry and the actual application. And we are taking care of the whole process. So we understood that finding the right parameters was possible only taking into account powders, the building process, heat treatment, and also the post-processing. So thank you very much for your attention.